Good morning, afternoon, night, everyone. Welcome to this interactive talk about how to reduce the cost of cloud infra. I'm the head of marketing at DevZero, and I will be moderating today's session. It will be casual, interactive, so expect some screen shares, slides, and real-world examples. By the way, feel free to drop your questions in the chat, and we will answer them live as we go. Devon, would you like to introduce yourself?
Yes. So hello, everyone. Thank you for joining. My name is Debo. I am the CEO of DevZero, and we're a platform for creating and managing developer infrastructure, which ends up supporting all the stages of the SDLC. I am an infrastructure engineer by training. Before DevZero, I spent 6 years there. So yeah, thank you for joining.
And Neil, what about you?
Hi, everyone. My name is Neil Master. I'm the CEO and co-founder of Sedana. We're a solution for automated workload migration for CPU and GPU workloads. So we can migrate a container at the container level or at the Kubernetes level, and we can migrate running stateful processes from one instance to another without breaking anything. And we do that to improve compute reliability, cost, and performance. And my background before this is I've been a serial entrepreneur. My last company was in healthcare AI, which was acquired. And I started my career at the AI lab at MIT doing large-scale computer vision machine learning research.
Thanks, Neil. I would like to share with everyone our agenda for today. This is what we will cover. We will primarily discuss the infra cost problem, the biggest opportunities that we have to save on infra cost, and we will show you how you can apply these optimizations to some use cases in AI. And finally, we will show how Devo worked at Uber and how they approached their issue with infra cost. So let's start with the infra cost problem. And today we are talking about infra cost because cloud spending is over 200 billion right now and is growing 5x in the last decade. And for many companies, this has become a real problem. Is the top two expense right after payroll. But let's set the stage first about what is this session, because today we're not going to talk about the usual stuff like buying reserved instances or committing to Amazon Web Services saving plans or using various cost monitoring tools to track cost. Instead, I would like to ask Devon Neil to share with us why cloud waste happens, where are the primary inefficiencies, and how we can fix them. So let's start with my first question is for you, Devon. Why is infra cost growing so fast, and what are the biggest inefficiencies today?
Yeah. So Alberto, if you could please jump to the next slide. So the first thing over here is as follows, right? When we talk about the cloud, primarily we just end up talking about the hyperscalers for the most part, right? So that's where you have your AWS, GCP, Azure, Oracle Cloud, OCI, etc. At its core, each of these cloud providers, they have made it incredibly easy to deploy and scale up fast. So it's very easy for me to, let's say, build a little application and go to the AWS console, like, some ways to go and get that thing deployed. And whenever any sort of, let's say the application is running slow for whatever reasons, either I can go and fix the application or I can just click a couple of buttons to go and deploy more. So deployment, scaling it fast, very easy. But implicitly, these clouds, we don't have a lot of tools to better understand how to optimize the workloads that we are running for our end users. And once the workload is up and running, sure, there's always the easy button of upgrade or like create more replicas or more instances. But is there more of a fundamental issue here? The newer instances that I'm creating, are they truly being utilized to the max? Those questions, it's not very easy to answer with the tool. And so most teams, they might have an inkling that their cloud resources are overprovisioned today, but in order for them to truly right-size everything, those tools don't really exist. And again, even in the companies that kind of have an inkling that they have an overprovisioning problem, they don't necessarily have the right tools to go and fix those issues as well. So that's when I see, like, that's point number one. And then the second bit over here is, if you look at how applications run today, what I just covered was I'm an individual engineer, I wrote an app and I just did. But that's not true in most cases. We have teams, there's certain internal tooling, etc. in place, usually managed by the DevOps and the platform teams. If you are a normal product engineer, you go and build an application, let's say you make a containerized version of some way of like packaging up the application so it can run somewhere remotely. And that's where the DevOps and the platform engineering teams come. To create infrastructure, most things are still in the Terraform, etc. realm, EC2 instances or Kubernetes clusters, etc. provision, and then our containerized applications will just end up, or however the packaging is, the application is then run in those instances. And these configurations at its core, right? If you think about a Terraform apply operation or a helm upgrade -- install, whatever, those sorts of operations, they're fundamentally very static in nature. That config is only created and looked at based on what we think the application will utilize at runtime, not based on what the application is necessarily using every single second of its run. And infra fundamentally needs to change very dynamically. And the static provisioning nature of our compute today, it just doesn't keep up with. And so, Alberto, if you could also jump to the next slide, like over here we saw, okay, containerized applications based on Datadog's information, they have a pretty large underutilization problem. And at the same time, these days, there's lots of companies trying out various sorts of AI-related integrations. And as part of that, the costs related to GPU instances are also starting to scale up pretty rapidly. And if you look at the CPU world today, sure, with our Kubernetes, this, that, and the other, we have various avenues to actually go and share a single CPU across multiple different workloads. But in the GPU world, it's usually not as easy to enable those sorts of workloads either. And so normally, sure, if one instance has only 1, 2, 8, however many GPU devices attached to it, one workload will normally just hold on to that one GPU instance as long as it's run. Which fundamentally, again, if the workload isn't actively serving user requests at that point in time, it's just holding on to a resource, which fundamentally leads to, again, the underutilization. And so this gives you a sentiment about, okay, the application developers like writing software and the DevOps and the platform teams, they're ultimately responsible for going and running the software. And this disconnect between the two started to cause some issues, which actually leads to my third point. And then, Bert, if you could please jump to the next slide. On predicting resource requirements is fundamentally when the engineer is writing, I'll just take an overly simplified example. Let's say it's a simple Python method. When the engineer is writing the app, okay, it's a couple of handlers, this, that, and the other. When a user opens a website or makes an API call, etc., that's implicitly when your Python web app is starting to, let's say, load more things into variables, which implicitly implies using more RAM. Or it starts to do more compute operations, which fundamentally means you start to consume more CPU resources. What resources an application consumes or utilizes fundamentally depends on how people are interacting with that application at once. To my previous point, the static configurations that were applied when either the application was deployed, or even worse, when we are creating, let's say, a cloud VM resource, that just does not keep up. And at its core, we have all gotten very used to provisioning for peaks. And this peak, in some cases, can be because, I don't know, some applications see the spike on Friday night or Saturday morning. So we provision for that for the entire week. It's even worse if that peak happens once a month. Now we are wasting resources for the entirety of the month, except for when that peak happens. And so ultimately, the methodology or way of thinking that both Neil and I will be talking about today is ultimately in the theme of, I'm sure a lot of us have heard of this thing, the term serverless. And an example of that is AWS's Lambda, wherein just based on when requests, etc., are coming in, instances are scaled up, they scale down when the requests die down, so on and so forth. But moving to something like an AWS Lambda also has very fundamental framework changes, just based on how that overall product works. But why can't our cloud servers, our cloud Kubernetes things, this, that, and beyond, why can't they also behave in the same smart way that a Lambda does? Because at that point, if we are truly able to understand how a workload is performing real time, and then keep adjusting the resources that are available to it real time without actually going and blocking off resources for when we anticipate the peaks will happen, that will fundamentally solve for a lot of the inefficiencies that companies are experiencing in their cloud infrastructure today. So there is a fundamentally better way to manage cloud infra. And really looking forward to diving deeper into that today. Maybe Alberto will tell you.
Thanks, Devo. Neil, what are your thoughts? What are the biggest inefficiencies from your experience?
Yeah, it's really, I think Devo nailed the key points. And I would just emphasize that, one, it's just difficult to identify and diagnose the problem. So observability and monitoring is usually post hoc. It's looking backwards in time to see where your surprise compute bill came from. Why do people get surprised by their compute bills? Because it's difficult to identify these cost drivers. It can be difficult to identify idle resources. And then the second problem is even when you can solve this observability problem, there's a limited number of actions one can take to reducing costs. And most of these comes down to trying to predict what your usage is going to be in the future and trying to optimize your deployments ahead of time. And that can be a very difficult thing to do. And then what's making this all more complicated is as Devo had shown in the slide, as AI and analytics increases compute costs, people start to use GPUs, which can be 2 to 5 times more expensive. And then dealing with bursty traffic, all of those things make the problem even more difficult.
Yeah, that totally makes sense. So most of the audience, I know that they are really interested on the how they can apply these optimizations to the infrastructure. So that's the main question right now. Is let's get into the technology, and perhaps Devo, you can start with sharing your experience optimizing infra costs using things like dynamic scaling, workload migration, hibernation. Then Neil can tell us more about the safe migration workloads that he's working on. So let's start getting into the technology and how this works.
So Alberto, if you could maybe go to the next slide, I'll start with the concept of like dynamic scaling first, right? Let's take a step back. Broadly speaking, there's two classes of compute workloads getting provisioned at its core. Everything at the end of the day is a VM underneath, and a VM is ultimately just a computer that has its own operating system and a kernel. And then we run these things called containers, and containers might have their own OS inside, but they ultimately end up sharing the host's kernel. And in the container side of the house, what we normally see is Kubernetes is one of the main products that seems to be supporting a lot of the containerized workloads run by a variety of companies. And every hyperscaler cloud also has their own version of it. Like, for example, Amazon has this thing called ECS, Elastic Container Service, I think what it's called. And that's again, they have written their own scheduling, etc. logic. And so at the end of the day, you're handing someone containerized that a container, Docker essentially, and they will then go and run. And in the default VM world, could be managing workloads using Puppet, etc., where Again, you have a packaged up artifact, might be a Docker container, some sort of a binary, and then you just get a VM, run the application on it, and ingresses, load balancers, etc. They are all configured so that you can target, like you external or end users can go and interact with those applications. At its core, when we provision, let's talk about the VM use case once. Maybe during this webinar, I'll try to use more AWS terminology. AWS has EC2, Elastic Compute Cloud. And when you provision an EC2 instance, you usually have to, there are names like M5, 2x large, 4x large, and whatnot. And those are all predefined based on how many CPU cores you get, how much RAM you get, and what sort of network throughput, so on. So when we provision one EC2 instance, let's say that has 16 gigs of RAM and 4 CPU cores. Even if you're using half a core and let's say 10 megabytes of RAM, you are paying for the whole thing. So this is just the VM use case. Then when you go to Kubernetes, Amazon has a thing called Elastic Kubernetes Service, EKS. EKS ultimately, Kubernetes cluster needs nodes. And those nodes are again EC2 instances underneath. When we provision a Kubernetes workload, there are these concepts of like requests and limit that you can assign to each workload. And the request is ultimately, okay, when this container image is running, these resources are blocked off. No one else can access them. And limit ultimately says that it can like scale up to some of those things. And fundamentally, this is the problem. The request that we set, that is always going to optimize for what, let's say when a DevOps engineer is looking at the Grafana dashboard, okay, I saw this peak on that Saturday morning or a Saturday night. So that's what we'll set our request at. Because we always try to optimize to make sure that workloads always stay running. When we get to that time of the peak, we don't want our workloads to ever fall over. That's what drives this methodology. But ultimately, one of the things that we experienced at DevZero was most workloads that we see, they are all spiky in nature and they all differ from business to business. Instead of being dependent on predefined configuration, we can actually look at the underlying virtual machines or the containers to truly understand how many resources they are consuming, exactly how many resources are they requesting from the kernel, etc. And a concrete example of this is, let's say I'm running a simple Python. Currently, it's consuming 10 megabytes. When it needs more RAM, let's say adding new things to an array, it'll always go to the kernel and request more memory first. Being able to understand when a workload is requesting more resources, and at that time being able to grant it more resources as and when it's available. And this actually ties into the snapshot, migrate, restore stuff that Neil will also cover. Being able to truly understand what a workload needs, being able to give it those resources either on that node or moving it to a different node, that fundamentally starts to fight this inefficiency problem we see in the world. This captures a large variety of production workloads. And also note the same theories in practice apply to CI workloads as well. Anything that's running in some sort of a workflow pattern where we are always accustomed to going and predefining a set amount of configured resources upfront, irrespective of whether the final workload actually uses it or not. In any of those cases, everything we talk about today will apply. The concept of dynamic or automatic resizing. Then the second bit is around the theme of hibernation. Again, I can go and spin up, AWS has these things called automatic scaling. And I can say that I need 400 computers. And if one computer dies, Amazon will go and remove that computer and then give me another. So you always have these 400 computers. And that is, again, usually irrespective of whether the computers are actually being utilized or not. And the same theories apply to the Kubernetes land as well. The concept of replica sets is what they call. So I have one containerized application sitting behind, let's say, an ingress, and I go and tell Kubernetes that I need 10 replicas. So the request problem, the over-provision request problem that I was talking about in the previous point, now that just gets multiplied. So now I have 5 replicas. So if I was over-provisioned by 50% initially, now it's 5 times 50. So being able to understand exactly how a workload is being used, being able to automatically scale replicas, and also understanding when a workload is absolutely not being used and being able to hibernate it properly. And by hibernation, I don't mean just turning the thing off and like that's not good enough, because at that point in time, we also lose out on a bunch of context that might be stored in RAM, for example. So being able to truly snapshot a workload to be able to bring it back whenever it's necessary again by the restore operations, those are a majority of the bits that I'm really looking forward for Neil to cover short. And then Alberto, before I turn it over to Neil, one other thing was the workload migration component. And so these are some of the things that we start to see across a few of the companies that we get to work with at DevZero. The first example is a company just running normal containerized workloads. And again, because of the problem that we have, the disconnect between the platform engineering team and the people that are actually writing the apps and the end customers that are using the products, we always provision for the peaks. And by using this serverless sort of a mechanism where resources are only being allocated when the workload really needs it, you end up saving significant amounts of costs. And like the graph on the top right was actually the cost reduction that team started to experience was because as they were onboarding more and more workloads to DevZero, that became a multiplicative. And the one on the bottom right is, I already talked about CI. It doesn't just apply to production workloads, right? At the end of the day, everything is just a compute, even for CI. And there are many teams that are running their own GitHub runners. You might be using GitHub Central, GitHub hosted runners as well. At the end of the day, we go and say, hey, I need an Ubuntu XL or an Ubuntu X or I need a very big EC2 instance to run this job. Similarly, over there, can we get smarter about how resources are actually getting provisioned and automatically scale things down when they're not being used and scale things up when the workloads demand it, I should say. So, yeah, the bits we are going to talk about lives through all stages of the SDLC, concepts of dynamic scaling, and then in order to support it, hibernation and workload migration. Maybe with that, I can turn it over to you, Neil.
Yeah, Neil,
Sure.
it will be great to know your thoughts on the opportunities to save on infra costs, and I would really like for you to explain us in how the save, migrate, and resume workloads work. It will be interesting to know.
Sure. Just so if you think about it today, when people deploy workloads, you really have you deploy your workloads based on your prediction of how many resources you're going to need. And your options are, once you deploy them, you either wait for them to finish, or there's a failure, or you interrupt them and terminate them prematurely. That's really the options that you have. So you're in this constant game of trying to predict how much resources you should have, how many reserved instances, how many on demand. Perhaps you're using Spot, and you're in this constant cycle of trying to make those allocations match exactly what your workloads are. But that's very difficult, if not impossible to do, because you may have varying user loads and user demands. So what we introduce is this very powerful primitive. We can take a running container, the state from workload, and we can suspend it so that you can resume it at any time in the future. You can do eventual computing with it, or you can migrate it very rapidly so that you can resume it on another machine, which allows you to start to resize and bin tack those containers. So if you think about deploying 2 workloads, and what you find is that over time, each of them is using only 20 or 30% of the utilization of memory and compute for that instance. What you can now do is you can migrate one of those containers onto the instance that already has an existing containers. And now you have two containers running on one instance where both of them have sufficient compute capacity. And now you can destroy that that original instance. And you're in that very simple scenario, you've cut 50% of your costs. And this configuration, this actual scenario is very common. It's common because of utilization patterns change between day and night. It changes the user load, etc. And that's what we opened up. So now if you think about that opportunity, now engineers and users have a significant tool now in terms of the actions they can take when optimizing costs. And another area where we're finding, particularly with AI, is that cold start times matter significantly. And because as you're hosting inference, for example, you may spend a significant part of your time, anywhere from up to 20% of your total compute time, just starting and stopping instances. And if that's the case, if you can reduce your start times by half, and we can accelerate those between 2 to 10x, now you're shaving off a significant portion of your compute. And this is becoming really important. There was recently a really great blog post from Databricks that showed that, being able to accelerate the cold start saved them an enormous amount of compute time. So I'll just stop there to kind of just give you an overview of how this primitive of save, migrate, resume can lead to actions that can significantly leverage those costs. And that's an area that we've been working with DevZero on.
That's great, Neil. I really would like to know more about your experience with AI, because I guess many people in our audience working with AI workloads, inference, and large scale compute, which we know, as you mentioned, are a huge cost drivers. And these workloads require expensive GPUs, and dynamic scaling, which also makes cost management a real challenge. So I know that you work with research institutions and AI companies. So can you share with us an example of how they manage infra costs, and what's your experience working with them?
Sure, Alberto, I'd be happy to. I'll start with one example. There's three areas that we focus on: reliability, utilization, and cost reduction is the second, and then performance is the third. So we'll start with reliability first. So we're working with a major GPU cloud provider, and what we enable is automatic stateful failover, which means that, in the world of compute, you might see that GPUs can fail often, or a workload can fail for some reason. And even in the case of a catastrophic GPU failure, what we can do is we can take that running workload, it could be inference, it could be training, and we can resume it automatically on another GPU without losing any work. So from the last moment when the GPU failed, we automatically have a snapshot, which we then resume and continue running on that GPU. And that right there increases utilization and reduces costs. And it can really help for time to market when you're training models. The second example is cold start performance, which I talked about. Because we captured a state of inference, we were able to take large models like 70B, and we're able to accelerate them by over 2x in terms of the time it takes from booting it to the first token availability. And that performance, not only does it improve the performance and improves customer retention and customer experience, but it also reduces costs because, as I mentioned earlier, if you can accelerate cold start times, you improve your amount of utilization that you have for your GPU. You're spending less time on non-revenue generating operations and more on actually generating revenue. And then the last piece is improving utilization. So the ability to impact your compute workloads on GPUs, the ability to do hardware and OS upgrades without interrupting workloads. All of those improve your utilization. And from our customers' experiences, they can improve their cost between 20 to 80%.
Dale, do you have some examples about your experience with DevZero working with AI companies as well?
Do some work both with like AI companies as well as like companies that actually create these GPUs. And ultimately, the bits, again, as Neil mentioned, we use Sedana here at DevZero primarily to target at the problem space of how can we maximize resource utilization. And as Neil is also saying, right, to dive into let's say the cold start problem. Like ultimately, some application somewhere, let's say you load a model and then you load its weights, and all of this stuff is essentially ending up in GPU VRAM sum. Until all of this stuff is available, you can't, like, this is very similar to how a Java application starts up or initializes it. And till all of this is done, the application can't serve the first tokens, which is called ultimately the cold start. And so there's this side of the house, and the other side is when a workload is always tying itself to one GPU, like that device can't really, again, depends on the security posture, etc. But that GPU can't be shared across multiple workloads. So those are the areas that we try to focus on for the most part, on how can we actually start to share GPUs across workloads and taking similar themes. So thanks to nothing from Satana, how can we start to snapshot those workloads and actually hibernate them when they're actually not being used at all, therefore actually freeing up the underlying EC2 instances and whatnot. And again, very similar to the slides you were showing, maybe it was, right? And those are the things that ultimately drive those insane costs to go down.
I would like to ask you, how did Uber approach infra cost when you were there? Key lessons that you took from that experience, and perhaps something that you and I have discussed before is how infra cost is treated differently between production and pre-production workloads.
Okay, let me start by setting the stage. So I started working at Uber at a time when like the whole containerization trend was in its infancy. One of the, like, there were two options in the market back then. One was Kubernetes and the other was called Mesos. And like broadly speaking, at that time, the strategy was always break up or cleave off pieces of a monolith and start to make those things microservices so that the end user facing applications could still continue to operate. It wouldn't look like there's been any change made ultimately. And at that time, because we're moving, look at it from the perspective of the DevOps people that are actually running these applications, right? Because we're very used to like looking at static resources, and that same mentality continued into the cloud with how we started to run these containerized workloads as well. And the next stage of that was, okay, in the old world, maybe it was a very large VM. Now you can essentially get smaller pieces of VM that are allocated to each container instance. And whenever you want more resources, you also have to set the context or expectation with the engineering teams that, hey, everything we run on this infrastructure is actually completely stateless. For things that are stateful, we need to come up with other strategies. So that was, again, a big shift that had to happen. And post that, okay, you need more resources, just create more replicas. And you would always have to support some edge cases where some sort of applications would always need way more resources than the cookie cutter would actually provide. And then you would let them go and do those things. And at that time in the world, this is mid to late 2010s, Uber was also a company that was managing its own data centers and running its own complete infrastructure. So we had more fixed costs than in the cloud. The cost can be a little more linear in nature. The infrastructure teams would always then keep track of what sort of workloads or services are spending what sorts of, well, I guess utilizing what sort of resources. The whole service ownership construct would come in, and then you would talk to each of those managers and each of the teams and like, hey, this is what you're using. Maybe go and readjust some bits in case you're underutilizing some of the resources that you're actually provisioning. And that was the major workflow at Uber. Again, the state of the market today is somewhat different from that. But one theme that continues on is production and non-production workloads were still treated slightly differently because of the type of end user facing applications that you would. Production, we were always fine with provisioning for peaks, broadly speaking. I guess the problem is a little different today. But for non-production environments, it was always the theme of when things are not being utilized, We also learned the lesson that asking an engineer to go and turn off an EC2 instance after they are done working in it is never going to happen. Whenever you're on, hey, you haven't used this in a week. That's a great point, but I actually intend to use it next Monday. So then you end up running it through the weekend anyway, although it's not being utilized. That's a pretty common trend. And so you'd also build some tooling to be able to understand exactly when things were being used and not used, automatically like start to hibernate resources. And so, yeah, infra cost, broadly speaking, treated somewhat differently from non-production to production for dev workloads at the same time. And Uber's case, there were a lot of containerized applications running in production, about 5,500 microservices. And so dev environments, etc., had to be shared because getting everything to run in the yes would be untenable. Yeah. And maybe like Alberto, if you could also switch to slide 9 once, I can just talk through the pre-production and production construct a little bit better. Like over here, you can see in this slide, there are some sorts of workloads that are always consuming a set amount of resources. And then non-production workloads are usually the ones that will start to see things that are a little spikier in nature. For example, a build is being run or a certain compile job or a test. And at those times, you want to give it more resources. And at other times, you just want to take those resources away and have it be available for other workload streams. And if there are no other workloads that need to use those resources, you release them back to the cloud, therefore not spending them. So that's how pre-production and production would normally differ in terms of resource utilization. And then, Alberto, if you could switch to maybe slide 10 once, I can, yeah. So I'll spend a couple minutes talking about, let's say, the one in the top right. The use case was ultimately containerized applications are running on EC2 underneath. And as a result, once a month, a certain peak would happen. And as a result of that, because the engineer doesn't know exactly what minute the peak is going to happen at. Therefore, you end up provisioning for that peak for the entire month. Because the what if of when the workloads needs more resources, and if more resources aren't available to it at that point in time, the workload will fail. And that is a revenue blocking operation. Because the engineer is trying to protect against that use case, you end up provisioning for that peak. And essentially with DevZero, because even though we give our users micro VMs, they are all backed by very, very flexible compute underneath, using those concepts of essentially dynamic auto resizing. Just thanks to that and just running on DevZero, they managed to bring that cloud cost down significantly. And the graph on the top right is again another similar example of that. And the one on the bottom right, I think, is very interesting. Like there are people that use, I guess most of us use Git. And when you want to do CI, like the workflow product that GitHub supports is called GitHub Actions. That's what is on per CI. GitHub normally sells those by the minute. And you can tell GitHub, hey, I need 4 gigs of RAM or 8 gigs of RAM. Not, and GitHub will just charge you for irrespective of the reason. And then there are some, after those costs rise, many companies will start to enforce their GitHub actions using either EC2 instance or not. There are some companies that also like self-host the whole GitHub from a compliance perspective. And at that point, the next realization that happens, sure, you get an immediate improvement in the cost basis. But after that, you see, you leave instances running all the time because the same set of problems exist, right? You can't really predict when, let's say, Neil is going to send the next pull request and when the CI workloads will need to run. And normally spinning up an EC2 instance might take between 8 to 10 minutes. And so Neil will get irritated because he wants his test to run. And if it's not running, it's not good for the team. So we just leave these instances. And again, similarly, just by being a little smarter about how we achieve or approach problems of bin packing, which is putting a lot of workloads onto one computer. And when certain workloads are starting to spike up, give them more resources and or move them to a different computer without any sort of user. And I'm not saying things like you have to restart your CI job or press the submit button. It'll automatically just continue. Like imagine a fault. As I is going from 1 through 100. And if the workload happens to get moved over when it's on iteration 50, when on new computer, it'll actually continue from either 50 or 51, depending on when the workload starts. And so those are the things that we tend to target to fundamentally fight this resource utilization.
We have received some questions on the chat already, so let's get through some of them and also encourage everyone that now is the right moment to share more on the chat, and we will ask them to Devo and Neil. So let's start with the first one, and feel free to any of you or to answer this one, or we ideally will have the input from you both.
So I see the first question here. It says, what are the best practices for identifying the hidden cloud costs, specifically managed services like EKS or RDS? I am first going to focus on EKS and then on RDS because like the reason is storage system. Let's say you need 100 gigs of storage. Let's say you're actually storing 70 gigs of data. You'll actually continue to store 70 gigs of data irrespective of that bit doesn't change request to request. EKS, the problem over there is there are things like kube state metrics, for example. C-Advisor is a tool that consistently will tell you exactly how much every single workload is using on a pod basis or on a pod namespace basis. And that gives you a sentiment of, again, through the week, through the month, exactly how many resources are allocated in terms of requests. Limits, I guess that component matters a little less. And like based off of that, again, there are things like the vertical pod autoscalers and stuff, and those usually end up restarting workloads in order to apply a newer recommendation. And often like people don't enjoy that, right? You don't want your end user having to like resubmit an Uber Eats order. But looking there would be a good first step in that direction. Cube state metrics, it can be your best friend for EKS. And for RDS, again, look at the underlying resource utilization, the size of the RDS instances that you're running, and the amount of data that's actually being stored in there. And yes, RDS gives you things like migration, this, that, and the other, and it comes at a cost. So Kubernetes has also had a lot of very recent amazing improvements where some folks are actually running databases in Kubernetes in production. So that could also be a good way to manage some of the cloud costs on that side. Neil, I don't know if you want to add anything on this.
No, I think that summed it up really well.
What would you recommend as the easiest first step for a team looking to optimize infra cost?
Yeah, let's start to look at, again, Kubernetes. I'll start with what's available on the open source side first. And then both Neil and myself can talk about what we are doing in our respective companies as well. But Kubernetes, again, with 132, 133, making sure to always stay updated on the latest versions of Kubernetes, because most of the cloud providers and the managed Kubernetes that they support, they don't normally end up supporting things that are in an alpha or beta stage, especially on the extension side of the house. So concepts of in-place vertical auto scaling, etc. Those still won't be available in the managed Kubernetes versions. But as you keep the clusters updated, that's one good way to make sure you always have access to the latest tools. And then, like, once we have that, then figuring out different, like, for example, the C-Advisor, I'm a big fan of that. That's a great way to get to truth at all times. Then building some internal tooling on top to automatically go and right-size resources based on whatever Prometheus is saying at that point in time. Ideally, without restarting any of the workloads, that's how I would tackle this problem if I was to do it from scratch today. And maybe like to get in a little bit into like what we are doing. I'll let Neil speak first, and then Neil, maybe a couple words on like how like concepts of SMR, how folks that are looking to start both analyzing their cloud costs and then figuring out ways to fix those cloud costs, how would they approach things like SMR?
It's the key there is understanding your utilization, and really what SMR helps you do is the gap that we've talked about between what your currently deployed resources are and what your demand is, and making that elastic. So there's always some level of over provisioning, and the way to think about SMR is now that over provisioning that was very set in stone and static. Now you make that elastic, so you can elastically and dynamically rescale your resources using SMR as a core primitive. And one of the areas that really comes up there is that oftentimes jobs can be over provisioned, both in terms of the number of instances, but also the type of instance. And so where you start to use tools like C advisors to understand what is the actual utilization amount that you have, and should you be on a different instance, how can you better use your overall memory that you're paying for? And that becomes a key factor. And how do you do this in a way that is reliable and performant?
That's a great follow-up question for you, Devo. How do we know everything that we are doing here is reliable?
Yeah. So the approach we at least take at DevZero is like reliability ultimately comes from, there's a lot of tools, right? Even if you look at the Kubernetes, for example, like the container runtimes that are being used underneath, like the runtime class and what, like container, dependency, etc. And every single version with each of these tools, like whenever things change, that leads to potential areas of unreliability. And so at DevZero, how we have approached the problem is we just expose two separate interfaces for compute. Because like we just try to look at the cloud in a slightly different way, where nothing is static anymore and everything is dynamic at all times. And so we have one thing that's called a workspace, which is ultimately like an EC2 instance, I guess, which is just a micro VM instead. Again, runs its own hypervisor, has its own kernel. So it has everything that along these instances. And the second thing we have is Kubernetes clusters. Again, nodes, pods, all of those constructs apply exactly the same way. And underneath, we actually use Kubernetes to schedule all of these things, including, so a pod is actually a micro VM on the DevZero, because for isolation, et cetera. But from a reliability standpoint, the bits we tend to monitor are how long is it taking for workloads to actually get snapshotted? How long is it taking for workloads to get restored? And then there's a lot of tuning. Again, there are some folks that run their own version of DevZero. So a self-hosted DevZero, you can run it on your own AWS. And on a company-specific basis, there are a few knobs that can also be tuned based on how aggressive or conservative some of these automatic restore operations should be. So that's how we approach reliability. And like for what it's worth, we went through a lot of these efforts at Uber as well. Uber, like reliability and availability was obviously of importance. So the same principles are getting applied at DevZero now. Neil, anything you want to add?
Yeah, I would say, what's interesting about the way people think about reliability today is they over provision, right? You are either you have a stateless workload, and so you just over provision because you want to ensure that when there is a peak demand, you're ready to service that. And for stateful applications, the behavior is that you also over provision, and if there's a failure, you have to restart that job, and there is going to be some interruption. There's going to be some downtime, and then the question is how fast you can replace that. And this is to the point where the common rule of thumb, there's rules of thumbs and ratios that major companies use, where they say, for every workload, we're going to provision it 2-to-1 so that we have enough capacity. And in some cases, it's 3-to-1. And that's expensive, but it's important for those companies because they're providing mission critical services. And what what happens is save, migrate, resume, SMR ends up changing the game. And the reason why is that in today's scenario, when a stateful workload fails, you've got to restart it. So there's downtime. In the case of SMR, is if there's a instance failure or another failure of some type, what we can do is we can take the last instant that a workload was available and just resume it on a new instance. And so that increases the availability. It also increases the reliability. It changes the equation you then use for how much you over provision. You don't need to over provision by 2 to 1. And so whenever you're thinking about cost, you have to think about reliability. And there's usually a calculus there that's very expensive. And what we do is we reduce that calculus. We make it so that you can now get higher reliability at a lower cost.
Thank you both. I think we could keep asking more questions, but we are almost over an hour, and I think that's enough for today's content. I just wanted to really thank you both for attending and sharing your experience with us. Also for the audience that engaged with us today, and we can continue the conversation. Just connect with Devo and Neil on LinkedIn. Check out their websites, DevZero.io, Sedana.com. If you want to know more, just reach out to us and we can continue this conversation. So again, thank you both. Thank you, the audience, and we will see you in the next one.